depending on which data you use. So for this case, data is given. So you can then arrange the data in the form of case 1, case 2, case 3 for 3 different lengths or maybe more, and then plot the data on a single graph, and that will show you different kinds of interesting variations. And the way to do it is certainly to use a spreadsheet package, because otherwise calculating using just the hand calculation is simply tedious and meaningless these days. So I expect that you should try to do it at least for a few cases. And if any of you have plotted the graph, please feel free to send me by email, or you can show me in the next lecture and we can have a discussion on that. So we are going to talk about something different, and after that we can actually start solving practical problems. So this is what is called the fin efficiency. So one of the things with fins is the idea is we've got the fin, we've got this fin here. This is the uniform cross-section fin. We have taken rectangular. If we had taken a uniform cross-section, circular cross-section one, let's say tube, all the derivations would apply because we are using A and the perimeter. So it is independent of the shape as long as it is of constant cross-section. So a term, fin efficiency, so we have used eta F. It is defined that the actual heat transferred from the fin, okay, which we have calculated in equations 7, 8, and 9 for 3 different cases, divided by heat that would be transferred if the entire fin were at base temperature. It's very simple to understand that this is our base temperature T0. So had the temperature of the fin somehow was T0, and then the heat transfer would have been a lot higher because of the loss of heat, there will be the temperature drop from there to there. So this is an hypothetical situation where the temperature of the fin is so high that the heat transfer will be more. The practical kind of limiting case is if you assume that the thermal conductivity of the material is extremely high, nearly infinity, then what will happen? This temperature will be the same because there will be no conducting resistance. So that is the concept, that for a very high thermal conductivity material, the fin efficiency will be more like 100% nearly. But in general, it will be much less. So for the case of, say, case 3, which is the insulated tip fin efficiency, insulated tip with a finite length of the fin. So if we put the fin efficiency expression, so that was the Q expression, if I recall, that is equation number 9, I think. Yeah, that's equation number 9. So if we put the actual heat transfer for a finite length fin with insulated tip, so this is it, and divided by what would be the heat transferred if the entire fin were at temperature that. And that is clearly HPL, so P times L is the whole surface area, okay? And H is the surface heat transfer coefficient, and obviously theta 0 is what we assume that the temperature is there. So that's HA delta T. And then that is equal to, if we put all these things here and do a little bit of manipulations here, we can see that HPKA, and this one goes up, and some simplifications, it will come out to be equal to ML, where M is equals to square root of HP over KA, if you recall from last week's, from yesterday. Okay, so that gives a very interesting expression that efficiency of the fin for the insulated case can be obtained by this relation. We can do further simplification. Say if the fins are assumed to be sufficiently deep, in other words, Z is much, much bigger than the thickness, okay, then we can make a little bit further simplification. Then the heat flow becomes one-dimensional, and that's exactly what we have assumed, that the Z is so big that the sidewise variation is negligible and we can consider the heat transfer to be kind of one-dimensional. That's our concept. And the expression for ml in that case can be simplified. So if you write what is ml, so m is square root of hp over ka. That's how we have defined m. And you put that, and then what is p? 2z plus 2t. Yeah, so obviously one z at the bottom, another z at the top. So one t there and another t there. So 2z plus 2t is the perimeter, divided by what is the area? Area is the face area, or the area of heat transfer for thermal conductivity, the area perpendicular to the heat transfer. So that's A here. So don't confuse between this area and another area, which we will introduce in a second. So this is your KZT and then your L. So this is like this. And now if we make further simplification because of this condition that Z is much, much greater than T, and then what we do, we multiply the denominator at the bottom and the top by L to the power half, and then simplify, okay, which you can do easily. You can show that ML becomes this, 2H over Km, this whole thing square root L to the power 3 by 2. And I can see from here that if you remember from last week's, from yesterday's calculation, that M has a dimension of 1 over length. So this quantity is actually a non-dimensional quantity. Okay, you should also check here that if you put the dimension of H, dimension of K, and dimension of area, and then the dimension of length, you will find out that this is a non-dimensional quantity. And it is a very common thing in the case of fluid dynamics and heat transfer and thermodynamics, always trying to move towards some sort of non-dimensionalization of the quantities for a valid reason, which I shall explain again. You already know it. So in this case, this is your K times AM. After doing that, AM basically is the profile area, which is L times T, which means this area, okay, area on this side. So you've got A, which is the area on this side, and AM is the area on that side, okay, L times T. Is that clear? Any further question? Okay, so what we do, one of the common approaches, which I have mentioned already, that when you go and practice in engineering life, you don't really need to use all these messy equations all the time. People tend to use much simpler approaches. And one of the approaches is because the very fact that case 2 is a finite length fin, which loses heat by convection at the end, is perhaps the most common in all design applications. Because the fin is actually exposed to a convection environment. However, we have seen that for case 2, the calculations can be a little bit cumbersome. Now, to avoid that, the practical approach which people take is what we do. We say that we define we change the length. So length is this actual length. We change the length and increase it by half of the thickness, L plus T by 2, and we call it the corrected length. And if you use the corrected length instead of L and use the equations for the case of an insulated tip, which is case 3, or if we go back to the equations, is equation number 9, then the results are fairly close to what you would have got by.
Sir, একটা question ছিল স্যার।
হ্যাঁ বলো।
স্যার ক্যারেক্টারিস্টিক লেংথের যে সূত্রটা স্যার, এখানে এল তো স্যার লেংথ আর টি হচ্ছে থিকনেস, লেংথের সাথে থিকনেসের হাফ দিয়ে কেন যোগ করতেছি স্যার? একটু যদি আলাদা
এখানে length is just considered as a linear dimension, সেই হিসেবে এটাকে ধরা হয়। It's a linear dimension. Character length মানে শুধু length না, it can be diameter, it can be perimeter, some sort of linear dimension. ঠিক আছে?
ওকে স্যার।
এবং এটার রিজনটা হচ্ছে যে তোমরা যদি এটাকে যদি আমরা t/2 দিয়ে এক্সটেন্ড করে দেই, তাহলে কি হচ্ছে? তাহলে অ্যাকচুয়াল কনভেকশন সারফেস এরিয়া is increasing. Yeah, and it has been found that the concept lies in the fact that I've written it, that lengthening the fin by t/2 is assumed to represent the same convection heat transfer as half the tip area placed on top and bottom of the fin. Okay, again, this is an approximate method, and the corrected length LC is then used in all the equations that apply for the case of an insulated tip, which is case 3. Okay, এবং আরেকটু এটার মধ্যে যদি আমরা একটু অ্যানালিসিস করি, যে যদি এটা সিলিন্ড্রিক্যাল রড হয়, যেটা আমি বলেছি যে এই ক্যালকুলেশন গুলো শুধুমাত্র রেক্টেঙ্গুলার ক্রস সেকশনের জন্য না, ইট ইজ অলসো ভ্যালিড ফর for ping, where the diameter is constant. So এই ক্ষেত্রে তোমার corrected length would be the length plus and 1/4 of the diameter. So this is a linear dimension. As long as the dimensions are in meters, we can add them together. And the concept is again saying that if we add that little extension, then you have got a surface area for convection. So that convection is kind of equivalent to to considering this difficult case 2 scenario. However, there is a little bit of error, which is shown here. The error is small. By using this corrected length approach is usually less than 8% if this condition is valid. Okay, so you may ask, okay, 8% is not very small. Yes, I agree with that. There is absolutely no reason to say that this is perfect. However, the value of the age is subject to large variations in all practical scenarios. No matter what you do, you take the value of age, but bear in mind that value of the age can vary depending on plus or minus 10%, to even if you go to natural convection, there are situations which can be plus or minus 60, 80% variation. So having said that, we are engineers, we are practical people. We know the theory that these are the fundamentals, and then we are there and make a judicious comment, judicious judgment that what is the best approach. And this is perhaps, if you went for a theoretical research in heat transfer, obviously people wouldn't be expecting that we'll be making approximations. However, when you go to work in industries, I'm sure some of you would be working, then the idea is you need to do things in a very pragmatic way, especially when this is a design course. This is not just heat transfer basics. This is a design course. In the case of a design, you always have choices to be made. And for the case of a design, there is no just one definitive solution. You always have to make your judgment. So again, as I said, this is this is an approach which is very commonly, and I would say this is perhaps more common than using the equations. All right. But for your course, of course, you need to know the things because you are learning, and for learning, you need to know both sides. Okay. So we can actually make life a lot simpler. If you do example 1, then you will feel that, oh, it's not that simple. It's quite messy. And then if you come to this one, you will see, oh, this makes more sense. At the same time, we need to bear in mind that, yes, there is a little bit of uncertainty, but that is justified because the H value suffers from a big range of error. Okay? K value, you have no issues. Conduction, as I said in my first lecture, that conduction is an accurate way of, what you get in theoretical calculations and what you get in experiment, they match very, very close. But when it comes to convection heat transfer, the story is completely different. And that's the reality. And the reason for that, I've showed you the boundary layer and I've showed you all other issues related to that. Then you can easily understand why those variations could come in. এখন এই স্টেজে আর কোনো প্রশ্ন আছে তোমাদের? Because that's the kind of end of our theoretical discussion. Any other question? Okay, I'm assuming no. So let's move forward. আরেকটা টার্ম আছে যে ফিন সবসময় যে এক্সটেনশন দিয়ে দিলে হিট ট্রান্সফার বেড়ে যাবে এমন কোনো কথা নেই. I'll show you an example next week. Under certain circumstances, introducing the fin rather decreases, if I recall correctly, but certainly it doesn't help. So fin effectiveness বলে একটা টার্ম আছে যেটা ডিজাইনে খুব commonly use করা হয়, যে Q with fin and Q without fin, this ratio. So if you use the Q with fin, then obviously the efficiency of heat transfer, the AF is the total surface area. Yeah, that's simple. And H, and then theta 0. Okay, so let's say this is your heat transfer with fin, and Q without fin. What would have happened is HAB is the base area times theta 0. Okay, yeah, that's fine. So that means if you put the fin, then this is the total heat transfer. You may have other equations, obviously, and this is the heat transfer. AB is the base area. Let me just take you back to remind what is AB. AB basically means this area A. You go to the base, and this is the area through which all the heat initially goes out, which is the Q value. So what it says that's if you didn't have the fin, then what is the heat transfer by convection through there is basically HAB times theta 0. And it's clearly this quantity is more than 1. Okay, depending on the AF, of course, depending on other quantities, efficiency, etc., etc. So if we take AF equals to P times L, perimeter times the L, AB equals to A, then the fin effectiveness can be expressed. Again, we're taking case 3, I think. So it comes out to be like this. Okay, so tan HML over M, basically. This ratio should be as large as possible. Okay, if it is less than 2, it may be useless to add a fin. So, this gives you an idea that, okay, we want to add a fin. That means it needs some manufacturing issues. That when you manufacture that product, you need to have some mechanism by which you will add the fins. At the same time, it's a design issue, it's a space issue, it's a cost issue. It can be aesthetic as well. So before actually putting the fin there, you need to think carefully as a designer whether it is meaningful to add a fin. And one of the ways to look into the things is the fin effectiveness. Okay, so let's show you some more equations, and this is what I have taken. I know you cannot see it very well, and I don't expect you to see very well. However, what you can see that there are many different combinations, many different types of fins. So for example, this is the rectangular fin which you have done. This is the fin, well, this is a triangular one, it is a pointed one. And this can be, I don't know, it's a parabolic shape. This is a circular fin, cross-section is circular. And then you have got pin, you have got cone. So there may be many different kinds of sizes and shapes and different contours that can be thought of. And once those are there, you can do some tedious integration and differentiation, and ultimately you can get expressions for all of them. So for example, for this one, you get these, for triangular, whatever, and you can get efficiency expressions and so on and so forth. And I'm sure if you check other books, you will find many more different kinds of analysis available. Okay, maybe for a kind of hexagonal, pentagon, maybe bent ones. So there are theoretical calculations available. Not mathematicians, even just having the knowledge of basic integration and differentiation and other functions which you have done, I think you should be able to do many more kinds of analysis. However, I'm a practical person, and engineers are practical people. In practical situation, charts are more popular, and from designers' point of view. What designers would like to do, they would like to use charts rather than just using the theoretical equations. Okay? Again, I can reiterate, the uncertainty associated with convection coefficients does not always merit using a complex equation. I think that kind of summarizes the reason that why people go for slightly less accurate, but much more user-friendly approach, which people can remember. And also the chances of mistakes. So look at this equation. The chances of mistake, even if you are using the MATLAB or whatever, someone has to type in all these numbers. And it may be the case that there may be a mistake, and the silly error can result in many problems. But what happens in real life, in practical engineering, engineering design, design companies, what they will do, they will have already programmed these things in their system. Okay, so if you go and join the company, you will basically understand what is there, and then just type in the numbers and get the data, whatever you want. Then you would say, sir, why we are doing all these things? Yes, you need these things because as a designer, you need to be very innovative. Suppose there is some changes has to be made. Suppose a material which was used before and it's not available anymore, so you need to go for a different material. Suppose a manufacturing process which was there in order to make that particular design was available at a certain time 10 years before, but not anymore, so you want to use that. Perhaps you want to go for a 3D printing rather than just manufacturing in the traditional way. So there are so many changes happening in engineering all the time. And if you have to cope up with those changes, having this fundamental understanding of these concepts and some of the developments is always helpful. And that's why I mentioned that I'm not very keen that you remember all those equations. But if you do it once or twice in your leisure time and understand the fundamental methodology of how these equations were derived, it stays with you. And if it stays with you, if you want to make changes in future life, you can always do it. And this is what I call learning. Okay, so do you have any further question at this stage? Okay, no, if not, okay. If not, what I plan to do now, I'll do the attendance very quickly. I think this is the best time, and I've got about 9 minutes before I'll be cut off because I've got this time limit of 40 minutes, and then please be prompt, and then we will get back to some problem solving depending on how much time we have, and continue next week. Okay, so I'll start and be very prompt. Roll number 24, Apil Mahmood.
Yes, sir.
Roll number 58, Mahmoudul Hassan.
Yes, sir.
Farhad Inayat.
Present, sir.
Fahad Inayat. Roll number 1, Fahad Inayat.
Present, sir.
Okay. Roll number 2, Faisal Shuhab.
Present, sir.
Roll number 3, Salim Al Razi.
Present, sir.
Roll number 4, Sheikh Abdullah Al Kamal.
Present, sir.
Roll number 5, Tasbeen Al Shifat. Tasbeen Al Shifat.
Present, sir.
Okay. Roll number 6, Muhammad Tanvir Ahmed Hridoy.
Present, sir.
Roll number 1, Rasul Ahmed Bhuya.
Present, sir.
Roll number 2, Abdullah Zubair.
Present, sir.
Roll number 5, Alamgir Hussain Shoykot.
Present, sir.
Roll number 6, Shishir Khan.
Present, sir.
Roll number 6, Shishir Khan.
Sir, present, sir.
Okay. Roll number 8, Yasin Abrad.
Present, sir.
Roll number 10, Farhan Sadiq.
Present, sir.
Roll number 12, Mahima Ahmed Mim.
স্যার একটু নেটের প্রবলেম হচ্ছিল স্যার, ও ক্লাসেই আছে স্যার।
ক্লাসে আছে? আচ্ছা, ঠিক আছে, আমি ধরে দিচ্ছি। রোল নাম্বার 15, আব্দুল হাসিব হাসান জায়েদ। ওকে। রোল নাম্বার 20, শাফায়াত ইসলাম।
স্যার রোল 15 এর স্যার মাইকে প্রবলেম বলতেছে স্যার।
Oh, so many problems. Roll 20, Shafayat Islam, acho?
Yes, sir.
Roll 21, Sheikh Salman Rahim Rifat.
Present, sir.
Roll number 22, Niaz Muhammad Zahim.
Yes, sir. Yes,
Roll
sir.
number 23, Mustafa Zawad Itmum.
ইয়েস স্যার।
Roll number 24, Mashrur Jahan Nirjan.
Present, sir.
Roll number 26, Ragib Tahsin Rinat.
Yes, sir.
Roll number 27, Rahat Rahman. Roll number 28, Salehin Mustaqim. Roll number 29, Fardin bin Ashraf.
Yes, sir.
Roll number 31, Zamiul Haq. Roll number 32, Niaz Mahmood Onim. Roll number 33, Aisha Siddiqa.
Yes, sir.
Roll number 35, Sadia Islam Lami.
Yes, sir. Yes, sir.
Roll number 44, Shohag Jaman.
Yes, sir.
Roll number 45, Abdullah Al Farouk.
Yes, sir.
Roll number 46, Erin Jahan Ifti.
Yes, sir.
Roll number 51, Shikta Ahmed.
Yes, sir.
Roll number 52, Tanvir Ahmed.
Yes, sir.
55, Rokia Begum.
Yes, sir.
Roll number 57, Shabbir Ahmed Faisal. Roll number 44,
কাজ করতে না
আমার মাইক কাজ করছে না?
না স্যার
এত সমস্যা হয়ে যায় কি যে করবো? Let me just see if I can fix it. আর তো কোনো
স্যার
ও আচ্ছা আচ্ছা
স্যার ওরটা
আমারটা
একটু
কাজ করছে?
জি স্যার ওরটা একটু শুনতে কষ্ট হচ্ছে এটা
আচ্ছা কার কথা বলছো এটা? রোল নাম্বার 57, শাব্বির। আচ্ছা ঠিক আছে, আমি ধরে নিচ্ছি সব ঠিক আছে। রোল নাম্বার 44, অলিউল্লাহ সামির।
Present, sir.
ও আছে?
Sir, present, sir. 44 present,
ওকে
sir.
ওকে 48, শহীদুল ইসলাম মাসুম। শহীদুল ইসলাম মাসুম। ওকে, থ্যাংক ইউ ভেরি মাচ। আমি এখন সেকশন বি তে যাচ্ছি।
স্যার হ্যালো স্যার।
Naimul Hassan. No, I need to wait. Let me finish. Roll number 33, Naimul Hassan. Roll number 18,
48, sir. Present, sir.
Eta pore. Let me finish. Once I finish, you need to stop and come back at the end. Please be disciplined a bit. Roll number 18, Shanto Shaha.
Yes, sir.
Roll number 48, Mahdi Hassan.
Yes, sir.
Roll number 56, Rahel Imam Rocky.
Present, sir.
Roll number 3, K.M. Mahmudul Hassan.
Present, sir.
Roll number 4, Muhammad Mahbubur Rahman.
Present, sir.
Roll number 7, Shoaib Ahmed Opu. Shoaib Ahmed Opu.
Sir, ও সিএমএইচে অ্যাডমিট স্যার।
আচ্ছা ঠিক আছে, আমি এটা লিখে রাখছি। Roll number 9, Imrul Kais. Okay. Roll number 11, Sabiha Naurin Haq.
Present, sir.
Roll number 13, Onika Tabassum.
Present, sir.
Roll number 14,
sir.
হ্যাঁ রুল 7 তো আমি জানি যে ও সিএমএইচ অ্যাডমিট। শোয়েব আহমেদ অপু।
Sir, yes, sir.
হ্যাঁ ঠিক আছে, তুমি আছো? অপু আছো তুমি ক্লাসে?
Sir, জি স্যার আছি স্যার।
ও তাহলে বললো যে কে একজন তুমি সিএমএইচ।
স্যার আমি সেমি থেকে ক্লাস করছি স্যার।
ও আচ্ছা আচ্ছা আচ্ছা, আর ইউ অলরাইট?
স্যার আলহামদুলিল্লাহ স্যার।
আচ্ছা ভেরি গুড। রোল নাম্বার 14, নাবিলা কামাল নোভা।
Yes, sir.
Roll number 17, Saiful Islam Shagor.
Yes, sir.
Roll number 19, Abul Kalam Azad.
Yes, sir.
Roll number 25, Mustafa Rafid.
Yes, sir.
Roll number 30, Sakib Ahmed.
Yes, sir.
Roll number 34, Galib Yasar Rahman.
Yes, sir.
Roll number 36, Nusrat Jahan
Yes, sir.
Ramesha.
Yes, sir.
Okay. Roll 38, Mustafa Al Faisal.
Yes, sir.
Thank you.
Sir, 38 present, sir.
Wait a second. Roll number 40, Mahtab bin Rashid.
Yes, sir.
Roll number 41, Nuzhat Akila Tushi.
Yes, sir.
Roll 48, Fahim Faisal.
Sir, 42, fine, sir. Yes, sir.
42, yeah, that's right. Sorry. 43, Qazi Rubayat Hussain.
Yes, sir.
Roll 47, Abdullah Al Adib.
Yes, sir.
Roll 49, Nahin Ibn Akbar.
Yes, sir.
Roll 50, Zahid Hassan.
Yes, sir.
Roll 53, Nafiul Islam.
Yes, sir.
Roll 54, Syed Tanzib Mahmood.
Yes, sir.
Roll 58, Takvir Rahman.
Present, sir.
Roll 59, Mustafizur Rahman Joy.
Yes, sir.
And roll 60, Naimul Siddiq.
Yes,
Naimul
sir.
Siddiq. Okay, thank you. আর এখন দুই একজন বলেছো যে তারা পরে মিস করেছো, বলো কে কে বাকি আছো, আমি কারেক্ট করছি।
Sir, section A,
হ্যাঁ, সেকশন এ বলো।
roll 48, previous batch, sir.
রোল 48, কি নাম তোমার?
Shahidul Islam Masood.
শহীদুল ইসলাম। আচ্ছা, শহীদুল ইসলাম মাসুম, ঠিক আছে।
Sir, section
Okay.
28, sir.
28, সালেহিন মুস্তাকিম।
Yes, sir.
আচ্ছা, ঠিক আছে।
Sir, section A 32, sir.
32, নিয়াজ মাহমুদ অনিম।
জি, sir.
ঠিক আছে, ওকে, থ্যাংক ইউ ভেরি মাচ। তো টাইমিংটা ভালোই হয়েছে, বিকজ আল বি কাট অফ। কত?
Section B, rule 60.
রুল 60।
Yes, sir.
আচ্ছা, কি নাম তোমার? From engineering point of view, it is perhaps not always necessary, because using these cumbersome equations is probably a futile exercise, given the case that within that you have got the terms like H, which suffer from a large level of, the variation or uncertainty. So the approach taken is generally different kinds. So I shall show you those approaches. So before that, let's take a look at a little bit more practical scenarios. And you would certainly agree that, yes, this is a very, very common thing. You have seen in generators, electrical generators. If you look at next time to any generator, you will see that they have got a range of, this kind of circumferentially arranged rectangular fins, perhaps, maybe different shapes. And this is again very common, that you have got a circular one and the fins are actually arranged in a circular pattern. So there is no end to it. And this is where design got to be innovative. You need to think in your own way of putting things. Okay? So if it happens, then obviously all complicated relations come. And this is just an example of many different kinds of charts which are available for solving heat transfer problems. So for example, in this case, this is the fin efficiency eta F. And you have seen that the equations exist. Yes, we accept. But the way they have done, they have included a fin efficiency. This is a non-dimensional quantity. And this is also a non-dimensional quantity which we have derived already in our fin efficiency discussion. Okay, you remember that? So, and that's where LC is the corrected approach, or corrected length. And then all these data are plotted in a graph. And the advantage is, if you can put this kind of graphs, then basically you are putting all sorts of different shapes and sizes and designs and everything on one particular graph. So for practical scenarios, what you need, you basically need one graph. And then your job would be to look at how these quantities are defined. Say, for example, if it is a rectangular and triangular, this is the way you define your LC. For the case of LC, if it is a rectangular one, which we have derived and seen, L plus T by 2. Whereas if it is a triangular one, you just consider L. Because I think the logic is, because it is a pointed end, so towards the end, perhaps it does not really add anything. So your LC is got to be L. If it is a rectangular, then your AM is T times LC. So you first find out the LC and then find out that quantity. And for triangular, it is half times LC. Anybody interested to see how these things were derived, just go to the Hallman, look at the different references. These are not all included in reference or in Cropera, nowhere. But if you go and look at the original references of the journal publication, you can always find those things. Obviously, some of you may be interested, have a look. So if you know this quantity, so you go up, suppose your quantity comes out to be 1.5, and you go up for this shape and read the data from here. That's your fin efficiency. Okay, so fin efficiency is an important quantity because ultimately this is what you need in order to do the calculations in a simpler way. The other one is this. Okay, look at that. And this is again tells you why graphical approaches are quite often the preferred method of solution rather than just resorting to calculations and the messy equations. So this is the case of a cylinder, okay, a pipe, and on the pipe you've got these fins. Okay, if I just take you back and relate this to this is basically this story. So you've got a tube. So the tube has got an inner diameter of R1, and then you've got this circular, circumferentially arranged cylindrical tube with a radial fin of rectangular profile. So this is the one. And perhaps this is the case here. And then what you do, you define the thickness is the T, obviously, and then R1 is basically the kind of radius from the center to the outer diameter to the outer edge of the tube, and then you add L to R2, and that's your R2. And then you've got R2 minus R1 is your L, very clearly, and LC, you have to correct it because it's a rectangular one, so L plus T by 2, R2C is R1 plus this, and AM is T over LC, because these are the quantities you need for this case. And then you read out those. And obviously, depending on your R2C over R1, you get a series of curves. Okay? The reason being, the equation which can be derived for this case is really, really big. Really, really big, I tell you. I had the experience of doing one or two ones. And within that, it comes as a parameter of R2 over RC, R2C over R1. So you just choose that value and you get one set of equations. You choose another one, you get another set of equations and another set of equations. So to avoid those, what people do, well, these things are actually programmed and written down here. This is almost comparable to, do you remember the Moody's diagram, which you have used for different F factor, friction factor for flow through pipes? Do you remember that? Can you hear me?
Yes, sir, friction factor.
Friction factor. মনে আছে Moody's diagram, ওখানে loads and loads of curves ছিল. So it is a typical case with engineering. So if you know the R2 over RC, and if you know the value of this quantity, you go up and read out the efficiency from there. Okay? And one thing is obvious from here, that this is only about rectangular cross-section. If you went for another cross-section, you get another set. If you went to another one, you get another set of equations. All right? So this is the most preferred approach. So তোমাদের আর কোনো প্রশ্ন আছে এখানে at this stage? Otherwise, I'll move to one example. I'm not sure how much we can do, perhaps not a lot, but at least I should show you the example which you can try by yourself. Okay, So
এক্সাম্পলে যেতে পারি?
হ্যাঁ, আমি এক্সাম্পলে যাচ্ছি। So if you read this example, it's an aluminium fin which is K equals to what? 3 millimeter thick, 75 millimeter long, protrudes from the wall. Okay, so the base temperature is maintained at that ambient temperature. Calculate the heat loss from the okay. So I haven't given you the solution, but what you can do, we can use the approximate method, calculate the LC and M, and use Q expression for insulated T. Okay, so I think we're probably running out of time, so not much I can do, but basically, yeah. So it is. You may ask that what is the kind of? It is a rectangular. Well, the information is given here that you are asked to do it per unit depth of the material, or in other words, it is considered the depth is very long, very big compared to 3 millimeters. So clearly, this is a one-dimensional rectangular kind of scenario. So তোমরা যেটা করতে পারো, আমি একটু I can. So this is example 2. And example 3 is you will need to use the curves. So this is aluminium fins 15 millimeter wide and 10 millimeter thick are placed on a 25 millimeter diameter tube to dissipate heat. The tube surface temperature is 170 and the ambient temperature, calculate the heat loss. So this is much more practical because it is on a tube. Okay, so it is on a tube and you are going to calculate the heat transfer from there. Again, it's a solution, calculate the LCAM and other parameters, use appropriate chart. Basically, the chart would be this one. Okay, so this would be for example 3. So I think I need to stop now because we are kind of finishing. So আমি তোমাদেরকে আজকের up to this আমি যা যা পড়ানো হয়েছে I'll upload my presentation and I would expect if you have time please try example 2 and 3. If not, obviously I shall make time next week, next Sunday, to make sure we all understand the basics, and I plan to solve more problems with you during the class next week. That's my that's my to-do list. Our প্রথম যেটা বলেছি example 1, I would strongly encourage you all to do as much as possible and have a feel of the different things that happen for different end conditions. আর কোনো তোমাদের কোনো query আছে at this stage? Otherwise I'll be stopping.
স্যার আপনি যে সিটি বা টার্ম ফাইনাল বলেন এই ধরনের ম্যাথে কি আসবে স্যার? মানে
এগুলো এখনই বলা খুব মুশকিল, আমি এখনো তো কিছুই করিনি, আরো তো যেতে হবে। তোমরা পরীক্ষার প্রশ্ন আর একটু পরে আসো, we are not there yet.
Okay.
All right.
আসসালামু আলাইকুম স্যার।
ওয়ালাইকুম আসসালাম।